All right, so I'll be talking about continual robot learning. But first thing first, there are some next continual learning talks coming up at 1:30. And they will be downstairs at Salon 4. And don't worry about the time, I'll be there too. So we'll be finished before the next talk starts, okay? All right, so before we start the talk, I want to talk first about, to set the stage, my ambition, which will clarify a lot what we are trying to achieve here. So my lifelong ambition is to understand the general principles of intelligence, right? To really understand how animals behave, what governs their behavior, but in a general sense, in a computational sense. And in order to achieve that, the setup I choose is the setup of learning systems on mobile robots. So the question is, how can I build animal-like intelligence for mobile robots? So the idea is that if we can do that, if we can achieve such a system computationally, then we'll have a good enough understanding on how animals behave, how intelligence works. All right, so having said that, now let's talk about continual robot learning. So what do I mean by continual robot learning? So there are many things that can be said about both robot learning and continual learning. So these are the two parts of continual robot learning. But I'm going to give specific definitions of them. The specific thing about robot learning that I'm interested in is I want to learn robot controls for real robots as opposed to simulated robots. And I want to achieve it not through offline learning, but through real-time learning. So the real-time learning is about learning and interacting at the same time. Okay, so that's robot learning. So that's what I want to do. That's the robot learning part of continual robot learning. Now there's another part to continual robot learning, which is obviously the continual learning. So in continual learning, a learner is expected to not only learn in real time, but they are also expected to learn indefinitely. So you'll expect that they will be given a sequence of tasks, like we are often faced with. We have to solve one task after another. We would expect the same from robots, that they would solve one task after another. So, and that's also a typical setup that is used in continual learning research, that an indefinite sequence of tasks is given, and the learner is expected to do well on each of them as they arrive, and at the same time remember the past as they are necessary. Now, those two are the two parts of continual robot learning, but one thing that becomes inevitable in continual robot learning is the resource constraint. So when we are trying to achieve robot learning and continual learning on robots, they are not going to have computer clusters available to them. And even worse, when we are talking about mobile robots, then the learning has to happen using only the onboard computer. So in terms of computational constraints, we are heavily constrained, and that's what we have to face. So having that in mind, now let's look at the approach we are going to take. Our approach will be based on deep RL, which is a natural choice. It's suitable because RL leads to general computational solutions. And deep learning is also suitable because then we can learn the features and representations automatically from data. And here you can look at an example of generality. So we can use an RL algorithm to make a simulated robot here, a robotic arm, to reach that red dot there, right? So it learned from experience how to reach that red dot. But using the same algorithm, we can also achieve on a different creature this hopping behavior, learn how to hop. Or for another creature, learn how to walk using the same algorithm. So that's the kind of generality we are talking about. So computational solutions, spatial learning solutions, they tend to be general, and they can be used on multiple robot bodies to achieve this kind of behavior. However, one issue is that these deep RL demonstrations that we see, they are usually done using simulations. So they are done offline. So to be more precise, this is what I mean by offline. So what we need in the end for deep learning and deep RL is to train a neural network, right, an AI model that would be deployed. To the right, you can see the real world, right? So that's why we want to deploy it. And when we use offline learning, the issue is that learning does not happen when it's deployed. Rather, learning happens in a separate phase. So as you can see in the bottom, we have phase 1 and phase 2. So at an earlier phase, this AI model, separately from the deployment, it is trained using a large stored data set or a simulator. And that's when the training happens. So it's kind of happening offline in the sense that it is learning when it is not deployed. And it is, when it is deployed, it's not learning. So there is a clear separation between learning and deployment. So in fact, almost all AI that we hear about today, they are all offline trained. So we can call them train once AI. As opposed to that, this is what real-time learning would look like. So learning and interaction both are happening at the same time in the real world when it is deployed. So learning is happening when it is deployed. So that's what real-time learning means. And that's what we are aiming for. So here is an example of real-time learning. Cats. They're trying to learn how to walk on a treadmill. Right? So we can be assured that cats did not evolve with this particular equipment, and they are not using like cluster computers to learn it. They're learning how to control at the lowest level, right? How to control these joints, the muscle activations at tens of milliseconds in real time, based on low-level inputs such as vision and touch, and using only onboard computations. That's the nervous system. And that's what we want to achieve. Right? So we want to build robots that can learn like a cat using only onboard computations. Now our question is, can deep RL be used? Right? So the approach we are taking is deep RL. Can we use deep RL for learning in real time on robots under resource constraints? So that's our question. So keep that in mind. That's the question we're trying to answer today. All right. So in order to answer that, let's look at a typical deep RL algorithm more closely. Here is a pseudocode of a typical deep RL algorithm. And the main thing to see here is that there is a for loop. This for loop is stepping the agent through time steps of interactions. So inside the for loop, each like whole iteration is about taking one action. That's the main part. So we can call that like an action cycle is happening in each time step. And then the main parts we want to look at are the parts that are computationally expensive or memory-wise expensive. The first statement we have is about taking the action. So at a particular state, ST, which could be about just the low-level vision or the raw pixels. That is given to pi, which is a neural network, right, a CNN policy, to do a forward pass and in the end generate an action. We often call it a policy inference. So pi is the policy. So it has some computation involved in it, right? So it requires a forward pass. It has a CNN involved. So that's why it's in color blue, different from the other ones. And then the next two steps are just taking the next state and the reward by taking this action. And once we have the current state action and next reward and next state, we collect it together and then store it in a replay buffer. If you look at the top, the replay buffer is initialized to be an empty storage. But each time step, we are including these samples, these transitions, to, the consequence of which is that this replay buffer is going to grow larger and larger. So here is an issue that although storing that particular statement is not computationally expensive, but it's going to increase the memory over time. So we have a memory burden over there. And the next two steps, they are about learning. And they are quite expensive. Next one is sampling a mini batch, right? So this replay buffer is full of images. Typically, we would sample 256 images from the replay buffer and transfer it from the RAM to the GPU. It's actually quite expensive. It's often as expensive as the next one, which is using the batch to make a gradient update, right? So here the gradient is being calculated using the batch to update the weight. So those two are quite expensive. So these are the expensive parts of DeepRL. Now, notice that there is an alternative to doing this calculation of learning like this. Instead of storing the sample in the replay buffer, we could just use that directly to make an update, right? So the bottom learning update that we have, we replace that by using the most recent sample to make an update. And that would be called an incremental algorithm. So keep that in mind. So that's an incremental algorithm, whereas what we are looking at, it is a typical DeepRL algorithm that is using a replay buffer and mini batch updates. All right, so now let's look at what is the consequence of having replay buffers and mini batch updates. So here we are looking at the memory requirement of the different parts of this learning algorithm. So on the right, you have image-based, for image-based robot tasks. A typical policy, CNN policy, will take computation, memory in the order of tens of megabytes, right? So that would be the typical memory requirement of the policy. Whereas the replay buffer will take 3 orders of magnitude more memory, tens of gigabytes. And that's just for a single task. We're talking about a single task RL problem. If we are doing continual reinforcement learning, then the size of the replay buffer is going to increase linearly with the number of tasks. And this disparity also impacts our choice of computers that we can use for learning. So that's an issue. Second issue is with the computational requirements. So on the right, we are looking at the time it takes for one pulse inference on an edge computer, just a nano, small computer. Pulse inference takes tens of milliseconds, which is kind of okay because it fits the typical action cycle time of low-level robot control, say 40 milliseconds. However, the learning update on this edge device, it takes 2 orders of magnitude more time. It takes tens of seconds, which means that although you can take an action within the required cycle time, you will have to wait for hundreds of actions in order to make just one update. All right, so then we just talked about the main components of DeepRL. One is the performance component, which is the policy. It's really about generating the action, right? So the main part of your learner is to be able to act. So generating the action is the main part. There's a performance component. And the other component is the learning component, which involves replay buffers and batch updates. Now, you can already see that there is a huge disparity, right? So there is a small part to the performance component, and there is a big part to the learning component. Now, that would be a problem if we try to use DeepRL in real time. So we can already ask, why don't we use the other alternative we talked about, which is not use the replay buffer, but rather use the most recent sample to make incremental updates, right? To shrink or diminish the replay buffer and the mini batch. What will happen in that case? So what is going to happen in that case is that it's well known that DeepRL methods are going to fail catastrophically. When we try to make incremental updates, that is without learning, without replay buffer or mini batch updates, in that case, DeepRL fails catastrophically. So sounds like DeepRL, if we reduce it to fit within an onboard computer to learn in real time, we are going to have failure. So now the question is, if that is the case, then how come we are fine using DeepRL in simulations? How it doesn't fail in simulations? So let's have a look at what happens in simulation. Here, have a look at the time step here. So within one time step, a typical implementation of DeepRL will calculate the policy inference and the learning update sequentially, one after the other. And also, we can, at will, pause or advance the simulator. Right? That's an option we have when we are simulating. And that's why what we do is, when we are making this learning update, we keep the simulator paused. We do not make any advancement. And that's why it doesn't matter how big of a replay buffer or mini batch update we're making. It will always fit a single time step. Right? So that's why this computational burden is not visible when we use deep RL for simulation. We can always use expensive updates within a single time step. And in fact, making frequent update is essential for deep RL algorithms to be sample efficient. So all the nice learning curves that we see deep RL is achieving in simulations, they are essentially making about one update per time step, often times even more updates per time step. So that's the crux of the problem. So far I tried to convince you that this is how deep RL works. It is expensive in terms of memory and computation, and it sounds like it's going to be a problem if we try to use it in real time. Okay, so based on that, now I'm going to walk you through a series of works that we have done that try to address this issue. Okay, work one. Here, simple idea. The claim is that if we use an existing implementation of deep RL that does computation sequentially, first inference and the expensive batch update, we are going to miss the deadline for taking an action. And that may result in slow reactivity, even sample inefficiency. So that's almost obvious by now, given what we already saw. So this is what we propose. So simple solution, which is to have the policy inference and the batch update having both of them asynchronously. What this achieves is that at least the action cycle time can meet the deadline, right? So if I have a target action cycle time of 40 milliseconds, I can meet that. But there is one issue, which is that my update is still expensive, so I might not be able to make one update per time step. But we already noticed that one single update has two big components. One is the mini batch sampling, and the other is the gradient computation. And those two can be done asynchronously, right? While I'm making the gradient update, I can prepare the mini batch for the next update. So based on that intuition, we then propose to have full asynchronicity, have all three computation asynchronously. And if we do that, in some cases, we can even meet the goal of making one update per time step. Now, once we understand the problem from first principles, it's almost obvious what the solution is, right? However, more important is to use an experiment to validate. And this is what we use. So this is a real robot arm with 5 joints that we control by sending velocity commands every 40 milliseconds. So it's low-level control. And the goal is to make that red circle bigger on the right screen. So on the right screen, what we see is the image feed that's coming from the camera mounted on the wrist of the robot. As you can see, there is a camera mounted there. So bigger the red circle, more reward you're going to get. And we are learning from scratch using a CNN policy, using raw pixels. So at the beginning, we start with a random policy. Right? So obviously, it's not generating a goal-oriented behavior. After 60,000 steps, it got a little bit better, but still not fully satisfying, right? Sometimes missing the target. Now, after 180K steps, after 2 hours of learning from scratch, now it is reaching the red dot consistently. So this is what we achieve based on our full asynchronous system. Okay, so now this is what we ask, how these different architectures that we talked about. One is sequential implementation, and then there are 2 different asynchronous architectures, how they perform when we increase the complexity of the problem in terms of computation. So we have these three different tasks here. Same task with different computation. So on the left one, we have the baseline that we saw. And in the middle, we have higher resolution of image. So there will be more computations involved. On the right one, we have larger mini batch size. And on y-axis, we have return, higher is better. And the orange bar is the standard sequential deep RL implementation. And as you can see, when we increase the computation, its performance starts to drop. Whereas when we use full asynchronous architecture, it maintains the performance. All right, so that's the summary of the first work. So the lesson here is that when we're trying to use deep RL in real time, we are facing difficulties for the reasons we talked about because of this large replay buffer and mini batch update. But we achieved an acceptable performance by using a stationary robot. Remember, our goal was to use mobile robot. Instead, we used a stationary robot, and we used a powerful workstation to achieve this performance. And the workstation was tethered, wired directly to the robot. So deep RL in real time, it requires abundant memory and computation, and it's just a single task RL problem. So we are not even touching continual learning problems. So we are facing difficulties. It looks like it will be difficult to deploy deep RL on a mobile robot, which will only have an onboard computer. So that's the question we try to address in the next work. Work 2. So here we ask the question, how can we deploy deep RL on mobile robots? Now we have less computation, just an onboard computer. But we already had the understanding, right, that onboard computers, they are too slow or too small to have mini batch updates or contain a large replay buffer. So instead, this is what we propose. So there are two possible directions from here we could take, two alternative directions. First one is to not use replay buffers or mini batch updates. So that is to use incremental deep RL algorithms. Now, as I mentioned, that does not exist, in the sense that if we try to deploy an incremental deep RL algorithm to achieve control behavior, they fail catastrophically. So this remains unresolved, and this is something the RL people here, you can think about how to come up with an algorithm like that can really solve it. This looks like quite crucial for real-time learning on mobile robots. We instead take, in this work, the second direction, which is we still assume that there is a powerful workstation available nearby, wirelessly, right? So then our architecture will look like this. So we have on the left a mobile robot. This is the Roomba vacuum cleaner, or its research version here, Create 2. It will host an onboard computer, an edge computer, Jetson Nano, in a tethered way directly. And then there will be a powerful workstation that's on the right that will be available wirelessly. Now, the computations that we have for deep RL, we can distribute them in three different ways. We can have everything, the performance as well as the learning components, completely hosted on the onboard computer. But in that case, we will have to reduce the size of the replay buffer. We will have to reduce the size of the mini batch. Mini batch update is going to take a long time. And as I mentioned, it's going to have poor performance. The second option is having everything on the remote workstation. The problem with that is then the action is going to travel wirelessly between the workstation and eventually the mobile robot. So we will have to encounter latency issues. A third option is we will have the performance component, that's the pulse inference, on the Jetson Nano, and the learning components, the replay buffer as well as the mini batch updates on the workstation. So that way, at least we don't have the latency of the action. Right? The action will be directly sent from the Jetson Nano to the mobile robot in a tethered way. So these are the three different architectures we can have. And we do a systematic comparison. But in order to do that, we don't use a mobile robot. It's still difficult to do experiments with mobile robot. We still use the same robot we saw, a stationary robot, but we emulate what is going to happen when we use a small computer and use the whole agent within it. So that's the bottom one, onboard only. If we use it, that's the performance we see is the green curve. So that's what a catastrophic failure looks like. If you compare that to the gray learning curve. So the gray learning curve is unachievable using a mobile robot. In the gray learning curve, we have the workstation directly attached to the robot in a tethered way. Obviously, for mobile robots, you cannot have a workstation directly tethered to the robot. So, but that is kind of the best performance you can get at this moment. So as opposed to that, the green learning curve is a catastrophic failure. As I mentioned, if you have smaller replay buffer, smaller mini batch size, your performance is not going to be good if you are using DeepRL. And the orange curve is where we have the remote-only architecture, where we have everything hosted on the workstation. The action is flying over Wi-Fi. In that case, we have much better performance than onboard only, but we still are performing poorly compared to the baseline. Now, if we use the other option where we are distributing the computation, the performance element on the onboard and learning component on the remote computer, in that case, we almost recover all the lost performance. Right? So the green curve is doing almost as good as the baseline. So that looks like is the best option. Right? So the latency of the action matters a lot. But we are still suffering a bit by using a remote computer for the learning updates. Okay, so based on this, then we end up using this remote onboard architecture on the mobile robot. So here, we're looking at the Create 2 robot, where on top of it, if you look closely, we have a Jetson Nano that's going to do the pulse inference. And beside, we don't see it. On the right, there is a workstation. And this Jetson Nano and the workstation, they're communicating through Wi-Fi. So the workstation is hosting the replay buffer. Workstation is doing the mini batch update. And as soon as it updates the policy, it's sending it back to the Jetson Nano. And there is also camera hosted. And the pulse inference, here we are taking an action of controlling the velocity of the wheels of the robot every 45 milliseconds. And again, we are learning from scratch using a CNN policy. The goal here is to reach one of those green targets. And at the beginning, this is how it behaves using a random policy. So as you can see, it is not looking goal-oriented at this moment, right? It's just wiggling around. But after learning from 100K time steps, now it's consistently reaching the target. Right? So this is achieved based on our remote onboard architecture. So inference on the Jetson Nano, learning wirelessly at the same time in real time happening. Okay, so we can achieve that too. So this is work two. So what is the summary here? What did we learn here? Did we learn how to deploy DeepRL using onboard computers? Right, so for mobile robot, the answer is yes, if you still have a powerful workstation nearby. Right, so seems like we cannot get rid of having powerful computers nearby. And what's the main reason? Why we are stuck with having something that's in the end infeasible for deploying mobile robots, right? Mobile robots, they will be in many different situations trying to learn. You may not have a powerful computer available all the time. So the real reason is this replay buffer and mini batch update, right? This is a big problem. We cannot, currently DeepRL methods, they cannot learn without them. Why is that? We try to look for the answer in continual learning. In continual learning, for a long time, we have already known that there is this phenomenon of catastrophic forgetting, which is the issue that if you're learning from a number of tasks in a sequence, say at the 10th task, you're asking, okay, how am I doing on the first one? Turns out that when we are using backpropagation-based algorithms, they tend to forget the past learning. And now we also tend to forget, but not as much as backpropagation forgets. Backpropagation forgets catastrophically, just to say that like it really forgets a lot, more than it should. So that's the problem of catastrophic forgetting. And the earliest and the long-standing solution has been to use a replay buffer, which is to store all the past information and replay them repeatedly. Right? So you keep repeat them on and on so that you don't forget the past. For some reason, backpropagation is forgetting. So how do you remind it? To show, to represent the past sample again. Now, how is that connected to DeepRL? Well, the common thing between continual learning and deep RL is that they both use backpropagation, right? So backpropagation is somehow causing this forgetting. So that is involved. And another thing that is involved is that both face non-stationarity, right? So when you, in continual learning, facing a sequence of tasks, obviously now you're facing non-stationarity. After one task, there is another. So things are changing. Now in deep RL, also, even if you're given just a single task to learn from, the states, you have these state transitions that are not IID. They have this correlation among them. And at the same time, the pulse is changing over time, due to which the data distribution is changing. So for all these reasons, even in single task learning, deep RL faces catastrophic forgetting. And that's why, that's one of the main reasons why deep RL contains a replay buffer, right? Because it seems like if deep RL is also facing catastrophic forgetting, deep RL should use a way to remember the past, and the simplest solution so far is having a replay buffer, and deep RL is using that. All right, so now based on this intuition, in this third work, this is what we ask. If we are to use a small replay buffer, if we reduce the size of the replay buffer, by what other means I can remember the past? Because it looks like backpropagation is somehow forgetting the past. We need some other means to remember the past. What can we use if we are to use a small replay buffer, right? So, and for DQN, we notice that there is already something that is delayed, in the sense that it's containing more past information compared to its current network. That's the target network, right? So the target network is always delayed. So our idea is to use that to somehow regularize, somehow make the current key network remember the past. So the resulting algorithm we call ME-DQN is a memory efficient DQN. Its loss function has two parts. The first one is the regular DQN loss based on squared error. And the second one is where we enforce the current network to track the target network. This target network is delayed. It contains some of the past information. A very simple idea. And we are hoping that this would allow the learner to remember some of the past so that we can afford a smaller replay buffer. So this is what we see in experiments. So here on the left figure, you see the red one is DQN with a large replay buffer, 10,000 samples, and it learns quite well. But when we reduce the size of the replay buffer to 32 DQN, what you see is a catastrophic failure, presumably due to catastrophic forgetting. The replay buffer is too small. However, when we use ME-DQN with a tiny replay buffer, it appears to match the performance of DQN with a large replay buffer. Okay, so the lesson from this work is that it might be possible to actually have a small replay buffer if we have other means to remember the past. All right, so that's hopeful. So we are getting much closer to what we want to achieve. And what's next? We should just try something on the real robot, right? But instead, we found another problem with continual learning. So in continual learning, we already have this problem of catastrophic forgetting. But we also ask that, okay, so it's not just about remembering the past. When we deploy a robot learning system on a mobile robot using just onboard computer, we want it to learn indefinitely. But can backpropagation learn indefinitely? Right? So we never answered this question. So that's the question we try to answer here in this work. And unfortunately, the answer is no. This is what we see. So to illustrate this, we use this input permuted MNIST problem where the pixel order is scrambled once in a while. And as the pixel order is being scrambled, there's almost nothing to transfer from one task to another. There's minimal amount of transfer possible. So we are not much worried about catastrophic forgetting in this task, right? We can forget about catastrophic forgetting and just focus on whether backpropagation can learn well on each task as they are given. So on the x-axis, we have the number of tasks being increased. On the y-axis, we have online accuracy, meaning that we only care about the accuracy on the present task. But what we see is that backpropagation its performance is dropping. Now, why is the case? Is the task difficulty increasing over time? No, right? Because these are just different versions of the same MNIST problem. So they are of the same difficulty level. So if we look closely, this is what it looks like. At the beginning, task 10 and task 11, backpropagation is learning as well as learning from scratch. But later, at task 240 and 241, we see that it is learning much more slowly compared to learning from scratch or from the beginning. So there is a problem. It is not learning as well as it used to learn before. Its ability to learn is losing over time. So we call this phenomenon loss of plasticity. So backpropagation over time is losing plasticity. Now, we ask, like, why is that the case and how can we address it? Like, why backpropagation has so much plasticity at the beginning, right? So partly it should be about the random initialization of the weights. So that's the special thing we do at the beginning. And by doing that, we ensure that the features are diverse and they are quite plastic. They can be moved around quite well with updates. So at the beginning, we have a lot of plasticity, possibly due to this random weight initialization. So our idea is to make sure that some of the features are always drawn from the initial distribution throughout learning. If we can do that, then the learner will always have some features to use for learning on the most immediate task, right? It will continue to have plasticity. However, which features we are going to use to do this reinitialization? For that, we propose that we pick the most unuseful feature and then replace it with a feature drawn from the initial distribution. And the resulting algorithm we call continual backprop. So how do we figure out what is the utility or usefulness of a feature? So here we have UI, the utility estimate of the ith feature. And this is how we estimate. In order to estimate it, we look at how much this feature is used, which is the magnitude of the activation output, and how much this feature is useful, which is the magnitude of the learned outgoing weights. So together then, in a combined way, is saying how useful a feature is, a particular feature is. Now, if a feature is not useful or it's not being used, then we can safely replace it using an initially distributed feature. So that's the idea. And based on this idea, when we apply it on different problems where we clearly have loss of plasticity for backpropagation, as the backpropagation line is just going down, with continual backprop, either we maintain the performance or continue to improve performance. Okay, so that's the summary of this work, that we are trying to solve one problem, which is to avoid catastrophic forgetting, avoid having large replay buffer. We ended up finding another problem. And that's how research works often. But that's good that we knew. Otherwise, we will run our robot for a long time and later we'll see that it's not learning. And we'll be puzzled. So I should mention that there are a lot of works currently happening in the community trying to either understand loss of plasticity or try to address loss of plasticity, right? So there are different algorithms that are being developed, and a lot of activities are happening around this problem. So currently in the continual learning community, there are these two trends. One group of works are about addressing the problem of catastrophic forgetting. And another group of problems, they are trying to address the loss of plasticity separately. However, if I deploy a robot learning system on a mobile robot using onboard computer and run it for a long time, I would not expect that it will only encounter one of the two problems. It will encounter both problems eventually. So how do we address both problems at the same time? And that's what we address in the next task, in the next work. So work 6, in this work, we admit that, okay, so continual learning agents will encounter both loss of plasticity and catastrophic forgetting. How can we overcome them simultaneously? So in order to address that, we go back to the whiteboard and look at the backpropagation rules, right? So the algorithm. And I'm going to walk you through these. I don't have a pointer, but bear with me. So the first row, I have just the forward pass. So H is the input. So this is the activation output coming from the previous layer and being used as an input to the current layer. So that H is being combined with W, the weights, linearly to get pre-activation, which is on the right, you'll see that is being passed to the activation function to get the activation output, which will then become an input to the next layer. So this is just simple forward pass. Okay, the top row is just simple forward pass. Now at the bottom, we have backpropagation rule. And something to notice here. So we are making update based on the gradient of the loss with respect to the weight. Right? So that gradient is what we use to change the weights. Now that is being calculated based on the middle equation. We have on the very right H as an input times the gradient of the loss with respect to the pre-activation. So that's easy to calculate, right? So the gradient of the weight can be calculated by the gradient with respect to the pre-activation times the input. Now, how do you calculate the gradient with respect to the pre-activation? So that's the bottom equation. Now, let's focus on that. So that's the recursive equation. We calculate the gradient of the loss with respect to the pre-activation for the current layer based on the gradient from the upper layer. So that's why it's called a backpropagation rule, because you calculate from the top to the bottom in a backward way. Now, the main two parts here are this, the activation gradient we have as the first factor on the right-hand side, and the last factor on the right-hand side we have W. And this is the most important part. So here we see that we are trying to change a particular feature proportional to the magnitude of the outgoing weight. So think about it, what it means, right? So I'm trying to change ith feature, but I'm going to change it more if its outgoing weight has more magnitude. So that has a consequence. The consequence is that if on a past task, the ith feature was found to be useful, its outgoing weights are going to be larger, right? And in the next task, I'm going to change the ith feature the most because it has larger outgoing weights. So that's kind of counterintuitive. But that's how backpropagation works. So why is that? Because backpropagation doesn't have any commitment to whatever happened in the past. Its whole purpose is to reduce the loss on the current task. Now, this is not something we figured out for the first time. In fact, when was backpropagation invented in this form first? 1986. In the same year, actually, Rich Sutton wrote a paper pointing out this issue of backpropagation rule, that if we then if we learn on a number of tasks, this is what's going to happen. Okay, so what we are figuring out here is that backpropagation, the particular way backpropagation works, is responsible for forgetting. So understanding this is what we conjecture. We attribute cascadic forgetting to its smallest unit, which is the weights. We say that, okay, forgetting is happening to a large part because past useful weights are being overwritten and relearned when we are learning on new tasks. And at the same time, loss of plasticity can also be attributed to the smallest possible unit, which is the weights. The weights are becoming rigid to learning updates. So these are our conjectures. These are the reasons we believe to a large part cascadic forgetting and loss of plasticity happening. And based on that, this is the algorithm we propose. We call it utility-based perturbed gradient descent, or UPGD. So more useful weights are going to be protected more highly from changes. Right? If there is a weight that's more useful, we are not going to change it much. And at the same time, less useful weights are going to be perturbed to repurpose them for plasticity, to make sure that there are some features available, some weights available to learn. So based on that, this is our learning update rule. So if you look at all the terms until the gradient, so that's the backpropagation, that's the gradient descent rule. Right? So that's the usual update we will do, but instead we add a perturbation. This perturbation term ensures that for some reason, if we lose plasticity, which would be possibly because the gradient information is absent, we would still move around this weight through perturbation. But it would be problematic if we perturb also the useful weights. So that's why we have this 1 minus ui, this multiplicative factor. We call it utility gating. We apply it to make sure that the more useful weights are not being updated. So ui is a utility estimate, and it is scaled between 0 and 1. So then if ith weight is quite useful, 1 minus ui is going to be close to 0. So we are not going to make any update to that weight. Whereas if it is not so useful, ui is going to be close to 0, 1 minus ui is going to be close to 1. So we will try to change that connection either through gradient descent, but if we lost plasticity and we don't have gradient information coming, then we'll at least perturb it using this white noise. So our idea is that using this rule, we can address both catastrophic forgetting and loss of plasticity by protecting the useful weights and perturbing the less useful ones. And this is how we calculate the utility. So in order to calculate the utility, the definition we choose is based on like how much excess loss we are going to encounter when we take out a connection. Right? If ith connection, if the ith weight is quite useful, and if we take it out from the network, we're going to encounter more loss. So what is the excess loss? So that would be our definition of utility. And this we can use to order all the weights in the network. However, this is quite expensive, isn't it? Because for each weight, you will have to take it out once and do a forward pass to calculate the loss. So that's quite expensive, so we don't want to do that. Instead, we use a Taylor approximation. So that's the bottom expression where we only need the gradient term and the weight, and also the diagonal of the Hessian. Now, the diagonal of the Hessian can be quite expensive, but in our recent ICML paper, we show how this diagonal of the Hessian can be approximated well enough using the same computational complexity as of backpropagation. So we can also compute that term cheaply. So that allows us to calculate the utility, to estimate the utility in a cheap manner, to plug it in right there. When we use that, we go back to the input permitted MNIST problem that we showed, and again observe all the regular algorithms, ARAM, SGD, they are losing plasticity over time, whereas UpGD is maintaining plasticity. Also, shrink and perturb is another algorithm that just includes perturbation. That's also maintaining plasticity. So this is to verify that UpGD is working well on addressing loss of plasticity. And as I mentioned on this problem, there's not much catastrophic forgetting to worry about. So for catastrophic forgetting, we look at another problem where we permute the labels. So the features that we learn from one task, they are quite useful for the next task. So there is a high possibility of positive transfer. However, the algorithms that encounter catastrophic forgetting, they will not have an opportunity to transfer effectively. And that's what we see with ARAM, SGD, and even with shrink and perturb. Just adding perturbation is not going to help with catastrophic forgetting. So they are not quite improving their performance effectively, whereas UpGD continues to improve its performance, presumably because it is protecting its useful features, it's addressing catastrophic forgetting. And note that here we not only address both issues simultaneously using the same algorithm, this is the only one currently we have that can do that, and we achieved it without any replay buffer or mini batch update. All these experiments were run using incremental updates. It's streaming learning, right? So we are now much closer to learning stably and effectively without using replay buffers and mini batch updates. Obviously, we would like to see how it works on RL. So here we use an RL experiment, and we have PPO here. We use PPO on an extended experiment, meaning that it is run way longer than it's usually run. And when we do that, what we see is that PPO at the beginning learns quite well, and that's where we usually stop our learning. But if we continue learning, the performance drops. Now, why is that? The PPO does not use a large replay buffer. It has a small replay buffer, like 200 samples, not quite big. So it's probably not adequate. So due to stochasticity in updates, it can forget its useful policy from the past. But due to loss of plasticity, it's not being able to learn it back. So its performance is continually dropping over time. So we often call it the problem of policy collapse. So PPO has this problem. Now UpGD should be able to address it because UpGD can address both issues. And as you can see, if we replace Adam from PPO with UpGD, we see that it either maintains the performance or continues to improve. Again, presumably because we are able to address both catastrophic forgetting and loss of plasticity. Okay, so these are the works I wanted to share with you. We started with the goal of having continual robot learning, right? So using mobile robots and solely using onboard computers. For that, we noticed that DeepRL has this issue, and we want to address it by having incremental algorithms, and we are now much closer to it. So that's the main lesson. So in conclusion, then I would conclude by reiterating that DeepRL is promising, but too expensive for continual robot learning. And you may say that, oh, it is expensive today. Tomorrow, there will be computers that will be able to do DeepRL. But note that when that happens, we'll also have more things to learn from. So DeepRL, the baseline requirements of computation and memory of DeepRL is too expensive for continual robot learning, is the proposition. And we can have patchworks right around this problem to try to address it. But in the end, what we need is scalable incremental methods without forgetting or batches or buffers. And our recent advancements suggest that such methods are well possible. So we are much closer to that than before. And in the end, I would also like to point out that when we have that method, incremental learning method, this will achieve scalability to an unprecedented level. And scalability is not just about being able to use large computers. It's also about being able to use small computers, right? Not only about scaling up, but also scaling down gracefully. And when we have scalable methods, we wouldn't have to rely exclusively on subscriptions to get access to AI, that what we have right now. We would be able to learn our own AI using our own small computers when we have scalable methods. So the scalable methods will make AI accessible and cheap to all. So that's also the proposition. Okay? Thank you all for listening. Questions?
If you have any questions, please come to the mic.
I have a question. Have you ever considered, you had a picture of a sort of vacuum cleaner going toward a red dot. Have you ever considered running two separate RLs, one for vision only, which would calculate the position of the red dot, and the other driving the robot to go to an XY position? If you think about our own brain, the vision is very much separated from our locomotion. It seems to me that combining both vision and locomotive in the same RL would lead to confusion and difficulty like you're talking, instead of running two RLs.
Right, so the question is whether we could actually extract the features of the vision problem separately and use that for RL, right? So this separation would reduce the computation. However, note that there is always new things to learn about the vision, right? So this is as an example to show that if we want to continue adapting the learner's vision part, we would need to test whether it's able to do so. So this is an example of doing that. Here, we are trying to learn something that we can easily solve by other means, by locating where the position is. But a goal here is that if there is not someone available there to tell when it needs to locate something, how it would figure out on its own. So that's why we want to test whether these RL agents can learn from scratch from this low-level sensory information. So there is a role for learning based on this low-level sensory information in many applications, and that's what we are testing out here. Although in this particular case, you're right that we could actually use XY information by other means.
And use RL on both the vision and on the locomotion.
Yeah.
Hi, sir.
Hi.
Like, I have a couple of questions about the multitasking problem here. Like, do you think it will be effective to add the states to tell the agent which task you are currently in? Let's say to use integer encoding. And also, what are your thoughts about using meta learning for this multitasking problem?
Right. So yeah, this is an interesting question. So in the continual learning case, we have this sequence of tasks. Would it be useful to tell the learner about the existence or about the change of task using, say, an information given as an input as an integer, right?
Yep.
So that's a line of works many people work on, right? So the setup we used, it's called task agnostic setup. It means that the agent doesn't know when the task changes.
Yes.
And that's kind of the more realistic. It's understood, well understood, that it's more challenging setup. So giving this task information, someone has to do some work. Someone has to know when the task changes
Yes, sir.
to give this information. And we think that that is not ideal. In the end, we want the agent to figure out this change by itself.
I see. And yeah, what about using like meta learning for this multitasking problem? What do you think about it?
So meta learning can mean many different things. It's usually doing more than backprop. We kind of do that.
Okay.
The UpGD extension can be seen as meta learning. There are more to it, to meta learning, of course, right? Learning the step size is meta learning.
Yeah.
And doing other things such as identifying when the change happens, that could also be seen as meta learning. So those are all important. Note that more learning components we add, more expensive it becomes. So that's like, we have to be careful about adding more things to the learner.
I see.
As we can see that even the base learner is so expensive.
I see. Okay. Thank you.
Thank you.
Hello, thanks for the talk. This question actually kind of parallels nicely with that one. I was wondering, for in the implementation of UpGD, for the perturbation factor, is that a static value? Because I noticed it had the subscript per weight. Or is that learned, is it updated over time, or just sampled from a distribution?
No, it is drawn from the normal distribution for each connection separately.
At each update? Or,
At each update for each connection.
okay, cool. Thank you.
Hello.
Hi.
Hi. So my question was that, so in the last algorithm that you showed where you add a utility parameter in the weight update formula, right? So what I essentially see it is as you sort of, as the number of tasks increases, the number of parameters responsible for making a particular decision for some particular task sort of limits. And that's why it sort of has other weight parameters for other tasks, right? So do you think, like, in the process of learning more and more and more tasks, ultimately the performance will decrease because there will come a point where the balance will be sort of hampered?
That's a great question. So ultimately what we are trying to do here is to make a balance. We are learning from many tasks, so we want to allocate some weights to some tasks and some weights to some other tasks. So in the end, if we see indefinite amount of tasks, what do we expect from a learner? So I would say that the main thing we expect from the learner is that it should do well on the current task. It should not lose the plasticity, which means that even though we have only a finite number, a limited number of weights, we should always allocate some to learn from the current one. And then the rest of them should be allocated in such a way that it remembers the useful past, not all the past that it predicts to be useful in the future. So it will have to then make a balance, right? So if it has, say, 10 weights and there are 100 tasks that are useful, it will have to only remember the top 10.
Yeah, that makes sense. Thank you.
Thank you.
Hello, thanks for the talk.
Thanks.
My question is, you talked about defining utility as the sum of the the magnitude of the activation. My question is, like, is there other definitions of utility, like how much the activation varies, the variance, the entropy, or is there work on that, or what do you think it's the impact of the definition of utility?
Right. So in the previous work, not this one, the previous work, we assumed we used a heuristic to define the utility to be proportional to the magnitude of the outgoing weight. And so that's one definition. Here, I would say that we are using a better definition in the sense that it's more based on first principles, which is we are looking at like how much loss that is being encountered when we take out a connection, right? So, and if you notice, when you approximate that, at the bottom equation, the second term has W squared. So this definition already incorporates the other definition, which is looking at the magnitude of the weight, right? W squared is going to be similar to the magnitude of the weight, but it has other terms. And there are, if you look at the literature, for pruning, people look at the utility of the weight, right? So they have to define the utility of the weight. And this is there's a vast literature on that. People use different definitions for defining utility. We actually compared a lot of them in this paper, and we showed that this particular definition, it correlates with the true utility of the weights much more closely than the other ones.
Very interesting. Thank you.
Thanks. Okay. Thank you, everyone.